So its position changing means that it's location, right? Another word for position here would be like its location, it's changing. If we started with our object on top of a building, right? If we started with a ball or an egg or something on top of a building, and that object drops, its new position is now at the bottom of the building or at the ground, right? Where its initial position was up at the top of the building, okay? It's just changing its location. When I say initial, do you know what that means?
First.
The first or the beginning, right? So if I say its initial position, I mean its position at the beginning of our problem. And then what would be the other term I might use? Not initial, but what would be the ending term? Final. Good. So I'll use initial and final a lot of times to describe how fast is it going at the beginning, or how fast is it going at the end, or where is it at the beginning, where is it at the end. We're going to have all those types of variables we're going to look at in terms of initial and final. So those are two terms that I need you to feel pretty comfortable with. Initial means at the beginning, and final means at the end. Do we feel okay with that? Right, the difference between those two? All right, so we talked about what does position mean. It essentially means its location, okay? So you might want to write that in there. Position means its location. Typically, our position is measured in meters, okay? It falls a distance of 10 meters, or it walked forward 3 meters, or whatever it might be. But position is going to be its location, right? Its change in location. And typically we measure that in meters. All right. We're going to focus our time right now in our introduction part is on straight line motion. So that means objects that are moving in perfectly straight line, either horizontally or vertically. So what's the difference between horizontal and vertical? Horizontal is like that, and then what's vertical? Up and down, right? Do we feel good about that? Because that's a commonly misunderstood vocabulary. Horizontal is flat, and vertical is up and down. And so our straight line motion is either going to be objects moving straight forward or backwards, or straight up and down. All right, motion always involves a place and a time. So we're always going to answer questions like, how far did it go? How long did it take for them to do that? How fast did it go? Those are types of questions we're going to be able to answer. Okay, so this is an example of extremely simplistic straight line motion. My car started at point A, and over a certain amount of time, it went to point B. Right? That's pretty boring motion, right? Simple and forward. But we can answer a lot of different questions about that if we're given some numbers. All right, so those are the types of questions we're going to start answering. How far did it go? How long did it take? And how fast was it going? Okay, those are the types of things that we're going to be able to answer. All right, how do we describe motion? All right, we've got two vocabulary terms here that we need to understand the difference of: distance and displacement. Okay, displacement and distance. Those are two ways that we can describe how far something goes, okay? And I'm going to talk about the difference in these two terms in a little bit, because these two terms mean very different things. But essentially, they're talking about how far, okay? So maybe you write a little extra note here. They're telling you how far something is going, okay? Again, we're going to get distinctions between those two words. They mean different things. I'll tell you that later. But it essentially means how far. And so we said that's typically measured in meters. Okay? Distance and displacement are measured in meters. All right. The next way we can describe motion is with velocity or speed. Have you heard those words before? Okay. Which one do you hear more often? Speed, right? There's a difference between speed and velocity, but in our everyday language, we tend to use speed more often. So velocity or speed tell us how fast something is moving. The unit for speed or velocity is typically meters per second. That's what that M over S. M over S means meters per second. Okay? So let's talk through what velocity means here. This means if I traveled 13 meters per second, for every second that goes by, I've traveled 13 meters, right? 13 meters per second. So after 1 second, I've gone 13 meters. After 2 seconds, how far have I gone? 26 meters. After 3 seconds, I've gone 39 meters, and so on and so on. Does that kind of make sense? For every second that goes by, I'm traveling 13 more meters. Okay. Have we done velocity before, or is this kind of new?
Yeah.
We've done it before? Yes? No? I'm getting yeses and nos. Okay, fine. All right. Last way that we can describe motion here is time, right? How long did it take for something to happen? Okay, we're telling how long it took for an object to do something. It is measured in seconds. That's really kind of an important note here. If we were given our value in minutes, we would need to convert it to seconds. Okay, same thing with this. If we were given our distance or our displacement in miles, we would maybe need to convert it to meters. Okay, and that's a good thing that we know how to do unit conversions already. Okay. All right. So today our main topic is going to be to distinguish the difference between distance and displacement. Distance and displacement. Both of those tell us what? Go back in that last slide. They tell us how far we've gone, but they mean different things. So we're going to talk about distance first. Distance is how many meters total that an object has traveled. And displacement is how far you ended up from where you started. Okay, do you see a difference in those definitions? Or do they seem the same? They kind of seem the same, don't they? But here's an example I want you to look at. Let's say that I start here. I walk 10 meters east. And then I turn around, I forgot something. And I walk 10 meters back home. What's my distance?
20.
My distance is 20 meters. But what's my displacement?
10.
Where am I starting? Where did I start?
0.
Right here. And where did I end up? Right back at 0. So my displacement here is 0 meters, right? It's how far I ended up from where I started. Does that make sense? Do you see the difference between those two definitions? How far I ended up from where I started. So there's a really big difference in those two things. I know I feel like I'm saying every word that starts with D ever right now, but distance is the total amount of meters that we walk. Displacement is how far we're ending up from where we started. Okay, and we're going to see a difference in those. So let's look at this coordinate system right here. Do you know what I mean when I say coordinate system? This coordinate plane right here? Do we feel good about positive, negative directions there? Okay, on a coordinate plane, this direction is positive, positive, negative, negative, right? What's this center point right here called? That 0, 0 point. What's it called? The origin. It's called the origin. Okay, that center point is called the origin, and that's when both our x and our y's are equal to 0. So we need to know from the origin, moving up is positive and moving to the right is positive. Moving down and to the left are negative directions. Okay, we also think about it using cardinal directions. Do you know what the cardinal directions are? North.
South, east, west.
Yep, east, south, west. If you don't know the cardinal directions off the top of your head, if you can't look at a map right here and know which one's north, which one's east, make sure you write that down. Okay, because we need to make sure that we feel good about the cardinal directions. Okay, so if I says it moves east, you have to know which way that is. Okay? You need to know which way is east, south, north, whatever. Okay? So if I draw an arrow that looks like this, what would be my displacement here?
Negative.
Okay, negative how many?
3.
Negative 3 meters. Right? If I draw an arrow that looks like this, it means I traveled negative 3 meters. Okay, if after I did that, then I decided I wanted to go the other direction and I walked this way. Okay, those two things put together, what's my total distance that I walked here? 7 meters, because I went 3. Oh, no, more than that. Okay, so let's walk through this one. I walked 3 meters south. Then I decided to turn around and walk up to here, and I finished right here. What would be my total distance that I traveled? I walked 3 meters south. Then I walked 1, 2, 3. Then I walked 7 meters north. What's my total distance? 10. Right? My distance is 10. I apologize if someone already said that, but my distance is 10 meters. What is my displacement? Where did I start? I started right here. So what's my displacement? How far am I ending up? I ended up right here. My displacement is positive 4 meters, right? I'm ending up 4 meters above where I started. Can we see the difference there? Or do we still need a little more practice with that?
7 meters north is where you count up from there, right?
I started right here, right? I went 3 meters south, and then from there, I went 7 meters north. So I didn't start back over at the origin. So let me map that out again. Okay, I started at the origin. I went 3 meters south, and then I turned around and I went 7 meters north. So my final displacement is where I started to where I end up. Okay, do we see the difference there? Where I started to where I end up. Okay. All right. So let's see. How do we draw displacement? We draw displacement with an arrow, just like I was doing on that last slide. So we draw displacement with an arrow. Okay, and we try to draw them in a proportional scale. So that means if I had a displacement that was 2 meters and a displacement that was 10 meters, do you think those look like they're drawn to scale? Why not?
Because one's 2 meters and 10 meters is not. They're the same length, the one's way.
Yeah, right? I'm not showing the difference in the length. So what I would need to do, if one was 2 meters, my 10 meter one would need to look something like that. Right? I need to make sure that I draw them appropriately to one another. Okay, that's called drawing them to scale. Right? I need to draw them appropriately to one another. Okay? All right, let's talk a little bit more about displacement. That's really what we're going to spend our time working with in this chapter, is we work with displacement much more often than we work with distance. Okay? Displacement it's a type of measurement called a vector. Okay, it's a type of measurement called a vector. All right, and a vector is a measurement that has to have both size and direction. Okay, it has to have magnitude and direction. So let's talk about this again. A vector is a type of measurement. Displacement happens to be one of those measurements. Okay, so vectors, this big category of measurements, displacement is one of those types of measurements. It has to have what's called a magnitude, which is like the number, and it has to have a direction. So if I want to say that he walked 10 meters, that's not a vector because it doesn't tell me what direction he walked in. Okay, I would have to put 10 meters north. This would be a vector because this is what's called the magnitude, okay, or the size. And this would be the direction. Okay, does that kind of make sense? So anytime we're talking about displacement, we have to have a direction that goes with it. Have to have a direction that goes with it. Okay? If we know that our object is only moving horizontally or only moving vertically, we could just go positive 10 meters and that would count as my direction, right? Forward would be my direction there. Okay, so you can choose to use positive, negative, or the cardinal directions. All right? All right. So our direction can be positive, negative, or cardinal direction. That's what I just said. We draw vectors using an arrow going in the direction of the motion. And we draw vectors one right after the other to show our motion. Okay, so let me just give you a quick example of what that might look like. Let's say that I walk 10 meters east. Then I walk 4 meters south. Then I walk 3 meters west. Okay, let's just say I'm going to do that. Here's how I would draw those vectors. I start at the origin. I draw just a little origin there to kind of show that I'm working on a coordinate plane. Does that make sense? I'm showing that I'm starting at the origin, and I'm going to walk 10 meters to the east. So what direction is east? Left, right, up, or down?
Right.
Right. East is to the right. So I'm going to go 10 meters. And I draw it with an arrow, and I draw it in the direction of my motion. So there's my 10 meter. That's my vector right there. Then it says I walk 4 meters south. So I'm going to start at the end, and walk 4 meters south. Okay, do you see how I did that? 10 east, 4 south. Then what am I going to do lastly? 3 meters west. So here's my 3 meters west. And that's what my overall path looks like, right? I'm going to end up in this location right here. All right? That's how I draw my vectors to represent my motion. I walked 10, then I walked 4, then I walked 3 more. What I did not do is I did not walk 10, then 4, then 3, right? I don't come back to the origin every time. I start one right after the previous one. Does that kind of make sense? We draw them one right after the other. Okay. If I were going to ask you how much total distance did I travel here, what would you tell me? I would travel 17 meters, okay? My displacement here, we haven't figured out how to calculate that yet. But if I wanted to find my displacement, I would draw a line from my starting point to my ending point, and I would be able to calculate that value using some math stuff. Okay, but we're not going to do that right away. So from this diagram alone, you can't calculate the displacement. You could find the distance, but you wouldn't be able to find the displacement just yet. Okay? All right. Have you guys ever used Pythagorean theorem? You know what that is? A squared plus B squared equals C squared? A little bit? Maybe, maybe not. Okay, all right. I just was curious. That's how you would end up solving that. Okay? But we'll see how we get there. All right, the opposite or the other part of displacement is distance, and we said distance is different. Distance does not need a direction. So when we said we walked 17 meters, let me just pull that back up here. When I say I walked 17 total meters, can I give a direction on that? No. Because I walked 3 different directions within that description. Right? So within that 17 meters, I walked 10 one way, 4 one way, 3 another way. So there's not even a possibility I could give a direction. So distance does not include a direction. Okay, so maybe highlight that, circle that, whatever you want to do in your notes, but we want to make sure that we understand distance does not include a direction. Okay? All right. We're going to start putting some motion here into our coordinate plane. We're going to actually start drawing out some motion. So I got a spot for you to draw them as well. So this says he walked 4 meters north, then he walked 6 meters south. So let's go ahead and graph this together, okay? Where are we going to start our motion from? The origin. You can either draw the little cross there to kind of signify that, or you could even start your motion with a dot. Either way you want to do it is perfectly fine, just as long as you kind of know that's your starting point. Okay, he walked 4 meters north. So I'm going to go ahead and draw. What do I just draw a line? Yeah. What do I draw? It needs to be an arrow. So it's a line, but make sure you put that arrow on the end. Okay, and I'm going to get a different color here so we can just see the difference here. But he walked 4 meters north, and then when we start 6 meters south, we go back and start from the beginning like that? No, we need to start from where we ended. So I'm going to start back here. And I'm going to count 6 meters south. So there's 1, 2, 3, 4, 5, 6. Okay, you see how I just counted down 6 meters? 6 meters south from where he was previously. And then that says that's where he's stopping. So I'm going to put a little right there. Okay, in all reality, I need you to understand that this red one goes like directly on top. Right? It's not in a different... It's not side to side, right? He turned around and came straight back. Does that kind of make sense? Okay, so what is his total distance? What do you think? 10 meters. I would agree. We're just adding those two together. But what is his displacement? Is it still going to be 10? No, it's not going to be 0. It's not just 2. It's -2. Okay, so what we're going to do is we're going to check here. Here's where he started. Here's where he ended up. That's -2 meters. Right, he's 2 meters south of where he started. So -2 meters, or you could even label it 2 meters south. Okay. Is that feeling a little more comfortable seeing it come into reality here, right, with an example? All right, let's try the next one together. Troy ran 400 meters east, then he ran 800 meters west. Then he ran 400 meters east. What is his distance and what is his displacement? So does our graph here go to 400? But what could we do instead?
Go to 8.
Well, okay, it doesn't really go to 8. So what could we do?
We can make each one of those things go 5.
That's right. So instead of going to 400, we'll just go to 4. That's right. Okay, so we're going to go east first. So is that right or left?
Right.
Right. So I'm going to start here in the middle. Okay, and I'm going to go 1, 2, 3, 4. That's my 400 meters. Then it says he goes 800 meters west. So I'm going to count over how many? 8. 1, 2, 3, 4, 5, 6, 7, 8. And then it says he went 400 meters back to the east. So 1, 2, 3, 4. So where's that put him? Back to where he started. So what does that tell us about his displacement? It's 0 meters. But what about his distance?
16.
Yep. 1,600 meters. Because 400 plus 800 plus 400 is 1,600 meters. Right? I add them all up. That's his distance. Right? So isn't it frustrating to run a mile and then they'd be like, oh, you didn't do anything. You know, displacement 0. I think that's crazy. That's how it goes. Okay, distance ran is 1,600, but displacement is 0. All right, try the next one here on your own. Allie walked 10 meters north, then 10 meters west. What's the distance traveled? So figure out how can you show this on this particular graph, and then how we can answer the distance. So did you decide to treat each one as a 2? Right, 2 meters? Is that how you decided to draw yours?
I just did mine with the 1.
Yeah.
Oh, so you just went up here?
Yeah.
Okay. Okay, that works okay, but we want to try to use up as much of the graph as we can, right? By getting it, by zooming it in a little bit more. So I'm going to go ahead and go up to 5, like as each tick mark is worth 2 meters or something. So that's 10 meters north, then 10 meters west. So is west to the right or to the left? Left. So am I going to just go right here and go this way, like that? No, I have to add it from the end. Okay, so we can add up her distance here. And what is it? 20 meters. Do I need to put west or east or anything with that? That's right, because distance does not need a direction. Now, why can't I solve for my displacement? If I were going to find displacement, it would be a straight line from where I started to where I ended up. And I would be able to calculate that value. Okay, I'm not sure that mathematically we quite know how to do that yet. So we're not going to do that for right now. Okay, but my distance would be adding the sides. My displacement would be like a bird's eye view from where I started to where I finished. Okay, the shortest possible path there.